Okay, so today we're going to talk about how to find limits and justify those limits. We're going to talk about how to generate different iterations using fractals, more specifically the Sierpinski triangle, which is a very interesting fractal. We're going to be looking at the Sierpinski triangle, and we're going to be using that triangle to get to know a little bit more about sequences. So let's just review about what we learned in the last class. First of all, what is a sequence? Can anybody tell me? Anybody? Yes, in the back.
It's an ordered list of numbers?
Yes, exactly right. Very good. A sequence is an ordered list of numbers. Let me give you an example of what would be a geometric sequence. Is just basically a list. 1, 2, 4, 8, 16. Okay, so now we have a sequence. Now, in between each of these is what's called a multiplier. Now, the multiplier is what you multiply each number to get the next number. So can anybody tell me what the multiplier is in this sequence here?
2?
Yes, exactly right. The multiplier will be 2 because you're multiplying 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. Very good. And you can also do it the other way around. You can go from large to small. You go 24, 12, 6, 3. Anybody want to guess what the next number in the sequence is going to be? 3 divided by...
2?
Yes, 2. Very good. All right. So there we go. Now, next thing I want to talk about, and we should know this already, is the difference between an infinite sequence and a finite sequence. Can anybody tell me what a finite sequence is? What makes it finite? Yes?
It stops at a number.
Exactly. It stops at a number. So you could say that this goes all the way to, say, 254. Now, since that has an endpoint, that makes it a finite sequence. Now, if this were to keep going all the way to the number n, it would go into infinity, which makes it what? An infinite sequence. Exactly. So how do we write a summation in order to find out, say we wanted to find a certain number. I'm going to give you an example here. Let's have a sequence such as this. We'll start with 2 plus 6 plus 18, and we're going to keep going all the way to 162. Okay. Can anybody tell me what the multiplier is here from what we know from our previous knowledge?
3?
Yes, 3. Very good. So we're going to need to have a formula to find the summation. Say you want to find the fourth term. Now, I'm going to just write down a formula. Excuse me, I'm going to copy from my notes here. A sub n equals a sub 1 times r, and I'll tell you about what all these terms mean in just a second, to the n minus 1. Okay, so now let's find out what our values are. Now r is going to be our multiplier, which we already said was the number 3. Right. R equals 3. Now, a sub 1 is going to be our first term. Now what's our first term?
2?
Yes. A sub 1 equals 2. Okay, so now the question is to find the fourth term. That's going to be n is 4. N equals 4. Okay, so we got all of our numbers right here. We're going to go ahead and plug them into our equation right here in order to get our answer. So a sub n equals 2 times 3 to the power of 4 minus 1. Are we making sense so far?
Yeah.
Okay, so let me just, we're running out of space here, so let's just go over here. that's going to be 2 times 3 to the power of 3. Now, what is 3 to the power of 3? That's 3 times 3 times 3, which would be 27. So 2 times 27, we all know that number is 54. And that is our answer. And let's just prove that that is the correct answer. Our multiplier, remember, is 3. 18 times 3 is indeed 54. So there we go. There's an example of how to find the nth term in an infinite sequence. Okay. So I'm going to go ahead and erase the board here. So we can go ahead and talk about our next subject, which is going to be fractals. Okay. Okay. So first of all, what is a fractal? I'm just going to read to you the definition, the dictionary definition of fractal. A rough or fragmented geometric shape that can be split into parts, each of which is, at least approximately, a reduced size copy of the whole. A property called self-similarity. Now, self-similarity basically means you can take one piece of that fractal, and that one little piece will have all the information of the entire fractal contained in that one small little area. So a good example of a fractal is going to be the Sierpinski triangle, and I'm going to move right over here and show you an example. Here we have our Sierpinski triangle, and as you can see, each smaller triangle is basically a small version of the entire large triangle. And as you go smaller into each individual portion of that, each one of those would be showing the same property of self-similarity because they copy the same information as the whole thing. So as you go smaller and smaller and you create smaller triangles within those larger triangles, it keeps going on and on and on, basically into infinity, which is what's really interesting about this triangle. I'm going to show you another example here. Excuse me for 1 second. We'll show you some other versions of the Sierpinski triangle. Here is a 3D version, so you can really see as you remove triangles, you start to remove some of the interior volume. Although the outside perimeter still remains intact, it changes in that way. Here's another version of a fractal. This is a fractal fern right here. So you can do many different things, and inside of each one, if we could zoom in more, you'd be able to see that each one of those is repeating itself. This is a cauliflower right here, and you can see the pattern again within each one of the pieces is repeating itself multiple times, and the multiple iterations within each time that it's repeating. So that's a perfect example right there of a fractal. Here's another one that looks a little bit like a snowflake. They all have the same properties of the patterns repeating, and as I said before, the self-similarity within each piece is repeating itself. Okay, so we're going to go back to the board here, and I'm going to just basically give you an example of the Sierpinski triangle right now. We're going to start by drawing one big triangle here. Okay. Pardon my messy drawing, but we're going to do the best we can. Try to fill this thing in. Let's use this one. Okay, I'm just going to color in the interior of this triangle. And we're going to shade the entire area within it the best we can right now, in order to demonstrate and then from this point on we're going to do the iterations of the other Sierpinski triangle by taking out some of the interior area. Okay. This would be a lot easier if it were done in a computer graphic, but we're kind of doing it old school today on this lecture. So here we go. Okay. Okay, so you get the idea. We're filling in the inside of the triangle. Okay, there we go. All right, so what we're going to do first is we're going to create a point at the midpoint of each of the equilateral sides. Now, do you know what equilateral means? Anybody know what equilateral? That means that each side of the triangle is equidistant, basically, from here to here, from here to here, from here to here. Equal distance. So we're going to bisect each section. And once we've done that, what I'm going to do is very carefully remove the interior area contained within that area. Okay? And I'm trying to be as careful as possible to try to make this work. There we go. Okay, you get the idea. There we go. So there's our first iteration of the Sierpinski triangle. Now, we can continue to do that multiple times. In fact, forever, as you will see in 1 second. Because I'm going to do the next iteration right now. Once again, by going to the midpoint of each side, the equidistant sides of the equilateral triangle which we just formed. And once again, we're going to take out this interior section. Like this. Okay. Is this making sense so far?
Yeah.
Okay. We'll do it again. The next iteration. Midpoints. 1, 2, 3. 1, 2, 3. We're going to create that. Carve out. It's a little bit harder to cut out these pieces once they get so small. But, we're just trying to get kind of a general idea of what's going on. Okay. So now you're sensing a pattern here. I can continue to keep going with further iterations as we keep going down the line. And you can kind of see the self-similarity, meaning that this piece right here has all the information contained in the entire triangle. So as you keep going farther and farther down, the triangle continues to repeat. And if you zoom in, if we were able to zoom in, you see it repeating, 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 and keep going on forever. It's almost like an optical illusion when you see it. Okay, so let's go ahead and erase this. And we're going to talk about now how the Sierpinski triangle relates to what we've learned about sequences. Okay, so I'm going to draw a few triangles right here. I'm going to draw about 4 triangles, if I have the space for them. Okay. Yeah, they're not quite perfect, but close enough. Now we're going to label these with stage names. So stage, this is going to be stage 0. Next one will be stage 1. Stage 2. And stage 3. Now, this first one is going to be just a full triangle like we did before, the original triangle, with it completely filled in. I'm going to fill this in once again the best I can. Much easier with a smaller triangle here. Okay. Second triangle, we're going to do one iteration right here. So, let's go like this. Right? And basically you're going to have a chunk taken right out of the center. Okay, so now you've removed that center portion for this one. Okay. The third one's going to be one more iteration, so we're going to go ahead and do that. It's going to have actually another section that's been removed. Okay. So we're going to fill in these little sections. And you can kind of see the pattern here developing with each subsequent triangle. But you can see that the original triangle is a similar shape, but we're just iterating within that same area. Okay. Fill this in, and then we've got one more to go, and it's going to be the next stage. Okay. And kind of get the idea here of what we're doing. And let's see. Cut little tiny triangles in here. It's going to really get difficult to draw after a while. Okay. And then this area will be filled in, basically filling in the blanks in between each one. You kind of get the idea here of what we're doing. And to make it more interesting, you can also fill it in with different colors, as we saw in the illustration. Okay. And I will just do a few of these here for you. Okay. So you get the idea of what's going on here. We'll go ahead and fill these in just to make sure that we're clear on what's going on. Okay. Okay. So we got stage 0, stage 1, stage 2, stage 3. Now, we're going to label these with their corresponding area. Right? So, if this is area 1, this area is going to be 3/4 of this area because we're missing this center section. So 1/4 of the triangle is missing. So this is going to make this 3/4. What is this section going to be? Well, we're taking another 3/4 of the 3/4 we took here. So it's going to be 3/4. Okay, so we're going to continue to where we left off when the tape ran out a little bit earlier. So we were talking about the areas of each of these triangles. And as I was saying, the area 1 includes the entire triangle. And as you go down stage 1, you're taking out 1/4 of the triangle, so now your area is going to be 3/4. Stage 2, you're going to take out 3/4 more of what we had before, so it's going to be 3/4 times 3/4. And finally, stage 3, it's going to be 3/4 times 3/4 times 3/4. So you're continuing to take out more of the area of each of the triangles. Now, what do you notice about this number as we continue to go down through more and more stages? What's happening to the number? It's getting
Smaller?
smaller, exactly. The number is going to continue to get smaller and smaller and smaller until what?
6 times 0.
Well, not quite. It's not going to get quite to 0. It's going to keep going down and down and down and down and down, almost to 0, but not quite hitting 0. So that's something to keep in mind. Let's talk about the perimeter of each of these. Now, let's take this first stage. Your perimeter is pretty simple. It's just going to be the distance around this triangle on the outer edges, because the entire area on the inside is filled. Stage 1, you've also got this perimeter on the inside because we took out that chunk in the middle. So your perimeter is going to be that much more, and on and on and on. Stage 2, stage 3, the perimeter is going to continue to increase as the area decreases. So what you find eventually with this sort of thing is, with the Sierpinski triangle, is you're basically hollowing out the inside and creating a shape with very little area contained in a huge amount of parameter. So, how do we write this and generalize what's going on here? Well, you can write it like this. Here's our formula. And that would be the limit as n is going to infinity. Now, this is the symbol, as we said, for infinity, if it's sideways 8, of 3/4 to the nth power. So each power is what it's increasing by. So 3/4 to the second power, and then to the third power, and on and on and on. So that's your formula. And so you can say the limit is n goes to infinity of 3/4 to the n. That limit equals 0. So there we are. Now, let's talk about how we can see this graphically, shall we? Let's do a XY graph. 1, 2, 3, 4 is your x-axis, and your y-axis is 1, 2, 3, 4. Sorry, I'm kind of running out of space here. Okay, so if you were to draw this graph, it would look something like this. And it's just kind of a rough estimate, but you can see the line as it approaches, as it goes farther and farther along the x-axis, it continues to get closer and closer and closer to the axis, but never touching. Now, what do they call that when it gets close to the x-axis but does not touch? I'll give you a hint. It starts with the letter A.
Asymptote.
Right. You have an asymptote. An extra credit if you can spell that correctly, too. All right. So, and you can kind of verify this. If the graph is, when x is equal to 1, for example, y is going to be equal to 3/4. Stage 1, 3/4. When x is equal to 2, y is going to be equal roughly 9/16, and that looks about what it should be. So, and then you have a, when x is 0, y is going to be 1. So that's why we have a intersection right here of 1, and then it goes into negative territory beyond that. So that's basically the way that we'll find the limit using the Sierpinski triangle. And what we're going to do for our homework assignment is we're going to try to predict future iterations based on what we know. We're going to practice with the formulas, and we're going to basically kind of just rehearse and review what we know about finding limits using the Sierpinski triangle.